Imagine stepping into Mars. The red horizon stretches before you. But there's a problem. You can't survive out here. Galactic cosmic rays would bombard your body. Surface radiation is higher than on Earth. Temperatures swing from 20 degrees Celsius to minus 100 degrees Celsius. And dust storms can last for months. The only way forward is maybe to live under a rock. To build a permanent presence on Mars, we need protection from four big threats: harsh radiation, wild temperature swings, choking dust storms, and a paper thin atmosphere. These aren't minor inconveniences, they are survival ending conditions. So, where do we live? Luckily, Mars itself offers us a solution: lava tubes. Beneath its surface lie enormous lava tubes, caves carved by ancient volcanic flows. At the top lies regolith, a natural shield against radiation. Beneath it is a basalt roof, hardened from volcanic flows, providing strength and insulation. The hollow cavern is the ideal habitat zone, safe from surface extremes. The red veins are lava pathways that once carved these tunnels, while the rocky basalt floor offers a foundation for future habitats. In many ways, Mars has already built the shelter we need. We just have to adapt it for life. This is where my project comes in: regolith based lava tube habitats for Mars exploration. My project uses regolith based lava tube habitats for Mars exploration. Mars dirt or regolith may look like useless dust, but with the right technology, it becomes the foundation of construction. Its composition is primarily silicates, iron oxides, and sulfates. Using in situ resource utilization, robotic 3D printers could melt regolith into basalt bricks to form concrete walls. 2 to 3 meters of this compacted regolith can reduce radiation exposure to levels comparable to Earth. So, what does this look like? Inside our lava tube, we imagine a modular settlement: pressurized living quarters, greenhouses, labs for science, and community spaces. In our YSP team, I took on the role of a microbiologist. My job was to ask, how do we keep humans alive, healthy, and productive in this underground world? That means managing microbes that recycle air and water, engineering plants to grow in the Martian soil, ensuring food security, and human health in the microbiome. In short, while astronauts explore, I make sure their life support systems keep running, one petri dish at a time. Why does this matter? Survival comes before exploration. If we can't live safely, we can't explore, build, or dream. Lava tubes and regolith aren't just clever ideas, they may be the very reason humanity can take its first real steps on another world. By living beneath the surface, we turn Mars from a hostile wasteland into a potential home. We may not be living in shining domes above the surface, but in the silent darkness beneath it, protected by stone, sustained by science, and carried forward by imagination. The future of exploration begins under a rock. Thank you.
Good afternoon. My name is Romario Martínez, and today I would like to invite you to rethink how we design the space habitats. Uh, my background is sport nutrition, so I specifically work with athletes in the mountain. They perform in hot and cold environments, so there is a extremely uh, analogy with the astronaut. Actually, we can have the perspective that the astronaut is extreme, an athlete, an Olympic athlete, I think. So many of the ideas that I'm going to share today come from work with athletes in the mountain, work it with athletes in the altitude with low oxygen, with high conditions like hot and cold environments. And that's basically what I'm going to try to integrate in this presentation. I work under the mentoring of Jen Blanc, the Dr. Jen Blanc, and the project that we work during these last 3 months is using the AI tools to imagine future planetary habitats. Specifically, we develop an habitat for 100 people on Moon on Mars, and I choose the Moon. Um, I have I don't know if uh, something special about the Moon in many aspects. I can explain that, but that's why I choose work on the Moon. And first of all, before go deeper, let's let's think about how evolution shaped us. And we come from habitats where microbes were everywhere. The microbes, the air, the plants, all these organisms co-evolved with us around all this evolutionary process. Today, we live in stereo environments, we live in artificial environments, and this puts a mismatch between our biology and the evolution that change or shape our physiology. Uh, I bring to this presentation two frameworks or two concepts that guide the design of my project. These concepts are recently new. I found it in people in the research of the microbes and fermented foods, and I tried to implement in the design. Uh, these two concepts, one of them is the exposome, which are the total set environmental exposures from chemical, physical, and biological that interact with us through life, from pollution, from particles, from air, microbes, even the social aspects can be contemplated as exposome. And in the other side, we have the holobiont. We basically try to conceptualize the, the human and the microbes as a single unit. So when I think about the design of habitats in space, I think how we can put the holobiont or the human and the microbes in the design, in the center of the design of the habitat. So I think that uh, integrate these two concepts, we can predict or we can anticipate new hazards from polluted megacities to lava isolate lunar lava tubes or even in the deep space habitats. We need to think about how these environments are or how these environments imposed some hazards to our physiology. For example, in the low orbit, we can have the benefit of the magnetosphere. So, but we also have the problems of the microgravity. In the lunar surface, we have other hazards. In the lava tube, we have another hazard, but we can get the benefit of the shield of these caves under the lunar surface. And in the deep space, we have another set of hazards like cosmic radiation that it's I think, one of the aspects that can cause extremely damage to our physiology. Particularly, I am very interested how the deep space affect the mitochondria. And taking in account these aspects, we can refine the design of these habitats, trying to think how we can counteract all these exposures. So in the second part of the slide, I put space exposome, which is a relatively new concept to me, but guide all these presentation. I think that microbes are a factor, even are is extremely important to our physiology because link our inner biology to our external environments. The microbes co-adapt with us as the habitat change, even in space. We can see this in International Space Station, how all these sterile habitats can affect the immunity of the astronaut. So it's going to be very interesting how we can understand the microbes under this condition, under these different conditions. But also we can use the microbes to create new innovations like the 3D printing. How can we use the microbes to improve the strength of the materials created using regolite? How can we use microbes to create new uh, fermented foods in space using bioreactors, or even use synthetic biology? So the future is very exciting for the microbes, and I think the microbes are going to be a central part of our quest to achieve the deep space. And the moon, to me, it's going to be a good laboratory or a scenario where we can test all this technology. I choose lava tubes because I choose the moon due to the proximity to Earth because it's going to be easier try to arrive to the moon uh, in this context, but also trying to design an habitat in the lava tubes is going to be very hard logistically, but also going to put in, on test or will put in test the robotics and AI, because I think this is going to be key parts as the microbes going to be. Uh, in the in the project, I try to understand how can we use microbes in an early shelter and to create these uh, platforms. We can use microbes to restrain all these structures. In the lava tube habitat, we can use bioreactors. We can try to create this organic ecosystem or artificial ecosystem that mimics the natural environment. The 3D printing is something I am also very excited about because it's not just about print materials. We are going to be able to print a, a new set of pharmacos, a new set of pharmacy, I think. So that's going to be another set of, of aspects that going to be improved with the microbe because I really think about synthetic biology, take making a relation with the 3D printing in space. So it's going to be very interesting what we are going to find in upcoming years. Uh, Also, I try to apply the expo. Also, I apply the exposome concept in a daily life, and we work trying to understand. I work trying to understand how we can create a better habitat using food production with bioreactors. Maybe thinking about the space kitchen where we can print the food with these materials, these organic materials produced by the bacteria. Maybe we can have some VR technology. In my mind, we can develop a 3D printer that is connected with the family of the astronauts. So the family of the astronaut can design the food that the astronaut is going to have in the habitat on the moon. I also think that the exposome can guide us about other hazards like sleep disruptions, the circadian rhythm disruptions, and all these aspects related to the exposome uh, point to one aspect that I am also very interested is that the inflammation. I think the inflammation in the astronaut it's one of the top priorities for somebody of what if somebody wants to maintain the health of this person in space. So the exposome could be applied to create this new architecture, but also we can help us to adapt to these new environments, to these new hazards. Uh, this is basically what I have been working in the project. How can we use the microbes? How can we apply all these concepts? But the exposome goes beyond the space. We can use the same concept on Earth. I currently trying to help some communities to restore the ecology from fire or some disasters. So what I can see right now is that the technology that it's being developed to from the space can be developed, can be used in on Earth, and it's something that I want to understand in upcoming years. I hope I can develop a career at this point in from from space. And my take-home messages for this project is that we need to think about the human-centered design, put the astronaut in the center, not just create a spacecraft with all this technology and innovation that are sterile. We need to try to think well, to think as the habitat and like an extension of the astronaut, like a placenta where the astronaut receive all these nutrient, all this oxygen, all these vital aspects, but in an artificial manner. I think that the exposome and the holobiont are two concepts that could lead us to a new findings. And to me, uh, try to integrate these concepts in the exposome and the holobiont make me uh, create better questions about the space. Maybe I don't have everything figured out, but I think that I have better questions, and I will try to answer that question in the coming years. But this is something that I enjoy very, very much. Try to imagine the future, and interestingly, I can use all this information. I can use all these perspectives to in my athletes because I can change the word human and put athlete centered design, and I can start to design some context to my athletes. I can change the word human for a community, and I also can put the community in the center, put the microbes of the community in the center. It's trying to create uh, a better habitat for that community, athlete, astronaut. Is something that I really enjoyed. Uh, at this point, from analogs to community, the insight from extreme societies on Earth, I really think that the space will give us uh, innovation and technology that could help us to in the climate change aspect, even in aspect like uh, cancer, this all this set of disease that are taking down the humanity at, in these moments. So I really enjoy this work in this project. I am a sport nutritionist. 3 months ago, I didn't even know all these aspects, but the amount of knowledge that I get from all the perspective of from the community of Blue Marble uh, make me think about a career in this path. So this is my project. This is about what I do in the last 3 months. Finally, I want to thank you to the Blue Marble Space Institute and the community for the amazing support. To Dr. Jim Black and my internship teammates. This journey helped me to grow a lot. So thank you for your attention.